Good evening, everyone. I welcome you all to the problem solving session of the NPTEL course on ice engine and gas turbine. Myself, Pradeev E. I am one of the TA for this course. So today I have some problems on Brayton cycle and then about aircraft propulsion. So the first question: an ideal air cycle consists of isentropic compression, constant volume heat transfer, isothermal expansion to the original pressure, and constant pressure heat transfer to the original temperature. Deduce an expression for the cycle efficiency in terms of volumetric compression ratio Rk and isothermal expansion Re. In such a cycle, the pressure and temperature at the start of compression are 100 bar and 40 degrees Celsius. The compression ratio is 8 and the maximum pressure is 100 bar. Determine the cycle efficiency and the MEP. MEP is mean effective pressure. So to draw this cycle in a TS diagram, I can draw both in TS and PV diagram. So the cycle consists of an isentropic compression. So in isentropic compression in TS diagram will be a vertical line 1 to 2, whereas in PV it compresses to a curve like this. And then we have constant volume heat addition. So that is a vertical line in PV diagram. And in case of TS diagram, it is a curve, something like this. And then there is an isothermal expansion to the original pressure. So that means TS diagram, it is a horizontal line, and in case of PV diagram, it is to the original pressure. Original pressure is something like this. So comes like this. This is 0.4, and then constant pressure heat transfer to the original temperature. So constant pressure heat transfer to the original temperature. So that is 4 to 1. And here it will be something like this. Deduce an expression for the cycle efficiency in terms of volumetric compression ratio Rk and isothermal expansion Re. In such a cycle, some values are given. So volumetric compression ratio Rk is, it should be V1 by V2, and expansion ratio Re, isothermal expansion ratio is V4 by V3. Now we need to calculate the we need to get an expression for cycle efficiency. So cycle efficiency, we know that it is work output by heat input so here or it can also be written as 1 minus Q rejected by Q supply. So this would be easier to find. So here QR is between 4 and 1. So that is Cp into T4 minus T1, and Qs is heat is supplied in two process. So Qs is equal to Q23. There is a constant volume heat addition, and then there is an isothermal heat addition, that is from 3 to 4. Now, uh, once we get an expression for Q2 to 3 and 3 to 4, and then have everything in terms of RKRE, then we can substitute in the efficiency equation. Now we will write Q23, that is a constant volume heat addition. So 2 to 3, so then it should be Cv into T3 minus T2. And Q3 to 4 is an isothermal heat addition. And for that, the heat addition in isothermal process is given as RT3 ln of 4 by V3. So that is RT3 ln of expansion ratio. Now we can write expression for all the temperatures that we know. So T2 by T1 can be written as V1 by V2 by power gamma minus 1. So this is compression ratio power gamma minus 1. So T2 is equal to T1 into Rk power gamma minus 1. So then we can substitute this in the Q2 to 3 expression later. And similarly, T3 and T4 are same because that is an isothermal process. And if you have to write an expression between the pressure 2 and 3, then we can make use of the ice ideal gas equation. So that is P2 so this gives P2 by T2 equal to P3 by T10. So from this I can say T3 is equal to P3 by P2 into T2. Now again I have to express this in using compression ratio and the expansion ratio. So we had T2 by T1 is equal to V1 by V2 power gamma minus 1, and this can also be written as P2 by P1 power gamma minus 1 by gamma. So with this, using this expression, we can write Re power Re sorry compression ratio Rk is equal to P2 by P1 power 1 by gamma, because on the power also gamma minus 1 get cancelled. So then we can write P2 is equal to P1 into Rk power gamma. So this is a relationship between P2 and P1. Similarly, if we write the expression between 3 and 4 ideal gas equations, we have P3 V3 by T3 equal to P4 V4 by T4. So here the temperature T3 and T4 are same, then this will get cancelled. Then we will have we can write our expansion is V4 by V3, and that is equal to P3 by P4. So that means I can write P3 is equal to P4 into expansion ratio. Now, are there some pressure? P4 and P1 are same, right? So, P4 equal to P1. So that means P3 equal to P1 into expansion ratio. Now, using these two expressions, we can get a relationship between P2 and P3. So, if I calculate P1 from here, I will have P1 is equal to P3 by Re. So substituting this here, P2 equal to P3 by Re into Rk power gamma. So P2 equal to P3 Rk power gamma by Re. Now we found this expression earlier, so that I have the relationship between P2 and P3. So then I can get the temperature relationship using the compression and expansion ratios. So here I write P3 by P2 as Re by Rk power gamma. So then I would write T3 as Re by Rk power gamma into T2. So now I think here we had Q rejection is equal to Cp into T4 minus T1. So do we have expression between T4 and T1? So between 2 and 3 we have this expression. So this is also T4 because T3 and T4 are same. Okay, so now if I have to write QR, I can write CP into, it is actually T4 minus T1. So I can write C4 T4 from this one. So that is RE by RK power gamma into T2, and minus, I would have minus T1, but I can write T1 using this expression. Sorry, T2 using this, or T1 is a function of T2. So that is T1 is T2 into RK power 1 minus gamma, or I think it is simpler to write T4 also as a function of T1. So T4 is RE by RK power gamma into T2, and T2 is again RE by RK power gamma. So T2 will be T1 into RK power gamma minus 1. So now we will have T4 as RE by RK into T1. So Q rejected can be written as CP into, I have T1 common, then I can write RE by RK minus 1. So this is QR. Similarly, we can reduce the expression Q2 to 3 and Q3 to 4 uh, like this. So Q here I have T3. T3 I can write as this one. So Q2 to 3 is CV into T3 minus T2. So here T4 and T3 are same. So I can write this as T4 minus T2. Now T4 is this one, RE by RK into T1. So that is RE by RK into T1 minus, if I can write T2 also as a function of T1, then I need to use this expression. That is T1 into RK power gamma minus 1 into T1. So I will have CV into T1 RE by RK minus RK power gamma minus 1. So this is the expression for Q2 to 3. Similarly, I can write Q3 to 4, that is R into T3, R into T3 into ln of expansion ratio. Now T3, can I write T3 as a function of T1? So this is also T4 is also T4 is also T3. So this is RE by R into RE by RK into T1 into ln of RE. So now efficiency I will have sorry, 1 minus QR by Q source, and that is Q2 to 3 plus Q3 to 4. So this is 1 minus QRS. QR we have just written down here. So that is CP into T1, CP T1 RE by RK minus 1. And this one we have CV into RE by RK into T1 minus RK gamma minus 1 into T1, then plus RE by RK T1 ln expansion ratio. Now here I have all T1 common, so I can remove T1, then we'll be left with CP into RE by RK minus 1 on the numerator, and then on the denominator we have CV RE by RK minus RK power gamma minus 1 plus R into RE by RK ln of RE. Now I have all RK common, RK the denominator. So if I have to multiply this with numerator and denominator by RK, then we'll be left with CP into RE minus RK divided by CV into RE minus RK power gamma plus R into RE ln into RE. Now CP also I can write in terms of gamma. CP is, if I have to divide everything by CV, then I would have if I have to multiply divide the numerator denominator by CV, I will have CP by CV on the numerator, so that is gamma, and so this would be gamma into RE minus RK, and here I will have CV into RE minus RK power gamma. So then next I will have R by CV. I need to find what this is. So R can be written as CP minus CV by CV. So then I will be having gamma minus 1. So this is gamma minus 1 RE ln of RE. Now we have found the expression for the efficiency of the cycle. It is just pure algebra. You need to start with the main expression, that is efficiency is 1 minus heat rejected by heat supplied. Heat rejected is only in one process and heat supplied is in two process. So now this is a constant volume process, and then B equal to constant, and here it is temperature equal to constant. So then we should be able to write this in this expression from basic thermodynamics, and then it's all manipulation, like how we rearrange the terms using the expansion ratio and compression ratio. And then finally we arrive at this expression. Now we need to substitute some values and then find the output. In such a cycle, the pressure and temperature at the start of the compression are 1 bar and 40 degrees Celsius. So that is P1 is equal to 1 bar, and sorry, P1 is 1 bar and T1 is 40 degrees Celsius, and that would be 330 Kelvin. Then the compression ratio is 8 and the maximum pressure is 100 bar. Where do we reach maximum pressure? At 0.3. So compression ratio is RK is 8 and the maximum pressure P3 is 100 bar. determine the cycle efficiency and the MEP. So to find the cycle efficiency, we will need this RE, RK and all, and gamma, CV, those things are known. So here this one, we are dividing on this. So now RK is given, RE we need to find. For RE, we have this expression. RE is P3 by P1, right? So RE is equal to P3 by P1, and that is 100 by 1, so that is 100. Expansion ratio is 100. Now we can substitute this and the efficiency. Then we will have 1 minus 1.4 into RE is 100. 100 minus compression ratio is 8 divided by RE is again 100 minus K is 8 power 1.4, and then we have plus 0.4 into RE is 100 and ln of 100. Can you calculate the efficiency? Are you able to calculate this?
So I'm doing so. Sir, I'm getting minus 184.
Minus 184.
Yes, sir. I tried two times. Both same time, both same answer.
Oh, but I'm getting correct 51 point something. So this is 1.4 into 92, and then what is 8 power 1.4?
18.37.
Okay, 18.38 update. Then we have plus uh, zero point 0.4 into 100 is 40 into ln of 100. What is ln of 100?
4.60.
4.60. This is 1 minus 1.4 into 92 is
128.87.
okay. Then 100 minus 18.38,
81.62.
21.62 plus this is 40 into 4.60.
184.2, sir.
Now this is 1 minus 128.8 divided by summation of this 81.62 plus 184.2. What happened? 81.62 plus 184.2.
81.6, sir. I divided 188.8 and divided by denominator. I'm getting 0.48.
0.4. Oh, here 0.48.
Yes, sir.
Okay.
Yes, sir.
And then this is 52, right?
0.51.
48 is 52. So this is 52%. So the cycle efficiency is 52%. You are getting this, no?
Yes, sir.
So next is, you have any questions in the previous derivation somewhere?
Yes, sir. I need one more time explanation.
Sorry?
I need one more time explanation.
Okay. Okay. So this this you would have understood, right? The first process is from in the PV diagram. If we see, it is from 1 to 2. That is isentropic compression, and in TS diagram it will be a constant. It will be a straight line. Okay. And then from 2 to 3 the process is given as constant volume heat addition, and that is constant volume will be a vertical line in the PV diagram, whereas in TS diagram it will be a curve like this. And the third process is the isothermal expansion to the original pressure. So 3 to 4, the 4 will be in the level of 1 because that is the original pressure, and that will follow a curve on the PV diagram. And in case of TS diagram, it will be a straight line because it is a straight horizontal line because the temperature is constant. Y-axis is temperature. And then finally we have constant pressure heat transfer to the original temperature. So that is coming to the original pressure and temperature, that is the original state itself. So 4 to 1 would be a constant pressure process, that will be a horizontal line in a PV diagram, and in TS diagram it will be a curve, but it will come back to the original state, that is 1. But then why they have given this diagram, right? Okay, anyway, I think this diagram has nothing to do with this. And now our K is given as volumetric compression ratio, that is from 1 to 2, that is V1 by V2 is compression ratio, and RE is the isothermal expansion ratio, so that is between V4 and V3. Now we need to find the expression for efficiency. So efficiency can be written as we know efficiency is work done by uh, heat supplied, and here work done can be written as QS minus QR, right? The heat transfer should be equal to the work transfer. So change in heat transfer should be equal to the change in work transfer. So this can be written like this. So then it will become eta is equal to 1 minus QR by QS. Here heat rejection happens in only one process, 4 to 1, and that is in constant pressure. So we can write the QR as Cp into T4 minus T1 like this. And for heat supplied is in two process, 2 to 3 and also T3 to 4. In 2 to 3 the process is iso like constant volume, and 3 to 4 the process is at constant temperature. So now we need to write the expression for heat in both the heat transferred in both the process. So 2 to 3 is a constant volume heat transfer. So we can write it as Cv into T3 minus T2. And for 3 to 4, you would have got through this equation in the in the thermodynamics, like in constant temperature heat addition, the heat added can be written as R33L into ln of V3 by V2, the final volume by initial volume. Now this final volume by initial volume V3 by V2 is the expansion ratio RE. Now, now we have got all this expression. If you put this in the efficiency formula, we will get the answer. But we need to convert everything back to compression ratio and compression ratio and the expansion ratio. So that means all this V2, V3, T2, T3, everything has to be converted back to RE and RK. So that is why we have started this. Now, uh, starting from the known values, like starting from the first compression thing, T2 by T1 can be written as V1 by V2 power gamma minus 1. So this is that means final temperature after compression can be written as initial temperature into compression ratio power gamma minus 1 with this expression. And uh, we know T3 and T4 is an 3T to 4, I mean, process 3 to 4 is a isothermal process. So T3 and T4 are same. T3 is equal to T4. And this is one expression. And similarly, applying ideal gas equation for 2 and 3 process. 2 and 3 is constant volume heat addition. Then we will left with this expression P2 by T2 equal to P3 by T3. So similarly, then we got expression for T3 as a function of pressures. And next, this T2 by T1 is also the pressure ratio power gamma minus 1 by gamma. So then we will get P2 is equal to P1 into compression ratio power gamma. Whereas for volume, we got like this. For temperature, we got like this. So uh, then between 3 and 4 where the temperature is constant, we get a relation like this, and with this relation we can write expansion ratio is P3 by P4. So we can write P3 is because P4 and P1 are same, we can write P3 is P1 into RE and so on. So then for writing P2 we will have how did we get this? P2 is equal to P3 into, yeah, so I think from here, so from this one, P2 is equal to P1 power into R compression ratio power gamma. So that has become like this. P1 is, we know P1 is this expression. So substituting this we got. And similarly, like if you do many manipulations, then finally you'll be able to write QR as a function of T1 and the compression expansion ratios. And similarly, Q2 to 3 also as a function of T1 and compression expansion ratios, and Q34 also as a function of T1 and compression expansion ratios. So then substituting all this and cancelling out T1, then we will get some expression like this, and then we have RK common in the denominators, and then we remove that, and using this expression Cp by Cv equal to gamma and R by Cv equal to gamma minus 1 and all, we have finally got this expression. Okay.
Okay, sir.
Okay. Now we need to find the MEP. What is MEP? MEP is mean effective pressure. You would have learned this in MEP in, I think we had some problems of MEP in ice engines, right? And what is MEP? That is work done by swept volume. Uh, Here the swept volume is between is from V4 to V2 or 3. It is swept volume and work done we need to find. So we know T2 by T1 is equal to V1 by V2 power gamma minus 1. So T2 is equal to T1 into compression ratio power gamma minus 1. So T1 is 312, compression ratio is 8, power gamma minus 1 is 0.4. So we can calculate T2.
Plus 716.78.
716.7 Kelvin. Now if we want to calculate T3, we had an expression between T3 and T1. Yeah, so this one T3 is T1 into RE by RK. So that is T3 equal to 312 into RE is 100 and RK is 8. Can you calculate T3?
Sir, 3,900, sir.
Sorry, 3000?
900.
Okay, exactly it is 3912. Okay. Now, Q supplied is equal to CV into T3 minus T2 plus R into T3 into ln of expansion ratio. So, CV is 0.717, T3 is 3912 minus T2 is 717 plus R is 0.287, T3 is 3912 and ln of 100. And calculate this heat supply.
So 7,436.77.
7000
436.77.
kilojoule per kilo. And work done is efficiency into QS. Efficiency is 0.51 or 52 into 7436.8 work done.
So 3,867.136.
3008
67.136.
67, okay, kilojoule per kilo. So this is work done. Now we can calculate the PM or MEP equal to work done by V4 minus V2. So here we have seen earlier that we had an expression between volume 4 and 2. Okay. Actually, expansion ratio is RE is V4 by V3 and V3 is same as V2. So that is V4 by V2. So V4 is equal to V2 into RE. and V1 by V2 is compression interest. Okay, so V2 is equal to V1 by RK. Now, do we have value for V1? V1 value we can find, so that is specific volume. Given 1 bar and 40 degrees Celsius, we will be able to find V1. So here V4 minus V2 is V2 into RE minus V2. Okay. So that is NP is equal to work done by V4 minus V2. So this is work done by RE V2 minus V2. So that is work done by V2 into RE minus 1. Now V2 is V1 into RK, V1 by RK into RE minus 1. This is one. Now to calculate V1, it's all specific volume. We know P1, V1 equal to RT1. So V1 is equal to R is 0.287 or 287 into 312 divided by pressure is 1 bar. So that is 10 per 5. Can calculate the value of V1.
Zero 0.89, sir.
0.89 meter cube per kilogram. Now MEP will be work done by this. So we found that work done is 3867. That is 3867 divided by V1 is 0.89 divided by 8. So I can put 8 here into RE minus 1 is 100 minus 1, that is 99. So can you calculate this?
So 3,441. No, sir. Three- So 351.11, sir. 51.11.
3.11. So this is in kilopascal because we have put 3867 in kilojoules. So this is kilopascal. So that is 3.51 bar in effective pressure. Do you have any questions?
No, sir.
Okay. Next is some previous year assignment problems. For 100% propulsive efficiency, the jet velocity of aircraft is dash the aircraft velocity equal to greater than less than or none of this.
Sir, equal to aircraft.
Yeah, equal to. Which of the following aircraft has the highest propulsive efficiency?
Sir, scramjet.
No, it is turboprop. So first is turboprop, then fan, and then jet.
Sir,
After
turboprop is highest
sorry,
intake.
turboprop.
Sir, it is based for the waste volume intake of air, sir. The turboprop.
It will take more air intake.
Yes, sir. Propulsion efficiency, the scramjet will give the more propulsion.
Just the propulsive efficiency.
Yes, sir.
So propulsive efficiency means turboprop is that's the maximum. You can go through the notes once, videos. I think it would be explained.
Okay, sir.
Next is afterburner in a turbojet engine is always mounted at the exit of axial turbine, at the exit of combustion chamber after the nozzle none of fuel.
Sir, after the nozzle.
No, it will be at the exit of the turbine. So there will be a compressor initially, then a combustion chamber, and then there will be a turbine, and then there will be afterburner, and then there will be nozzle. This is important. So it is at the exit of axial turbine. Specific fuel consumption of an aircraft is defined as the amount of air required to generate unit specific thrust, the amount of thrust generation for kg of fuel, the amount of fuel required to generate unit thrust, the amount of thrust generated per unit mass per rate of air.
Sir, option B, the amount of thrust generation per kg of fuel.
Sorry, option?
B, amount of the thrust generation per kg of fuel.
No, no, no. It is amount of fuel required to generate this. So in SI engine we have BSFC, right? Brake specific fuel consumption, that is gram per kilowatt hour. Brake specific fuel consumption. So brake energy specific. So here it is specific fuel consumption is based on thrust. So that is gram per newton. So for every newton of the thrust that has to be generated, how much gram of fuel we need to give in. Next is arrange in correct sequence as per the flow of air through turbojet engine. Intake, air compressor, uh, combustion chamber, axial turbine nozzle.
Sir, descending or ascending also.
No, like starting
Okay,
from the
okay, 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 okay. Okay. Sir, Sir, option D 1, 2, 3, 4, 5, 6.
1, 2, 3, 4. D. Yeah. Which of the following aircraft has absence of rotary parts?
Sir, option D is ramjet and ramjet fielder.
Yeah. Turboprop engine deals with highest propulsive efficiency, higher mass flow rate of air, higher jet
Sir,
fuel,
option D.
highest prop. And it also has high mass flow rate of air, right?
Yes, sir, but not greater than the turbo fan engine.
Additional. Then arrange the following aircraft on the basis of increase in altitude and Mach number. Turbofan, turboprop, turbojet.
Sir, two option C, sir. 2, 1
2,
and
1, 3.
3.
Yeah. First is turboprop, which will go at low altitude, low speed, and then turbofan, higher altitude, higher speed, and then turbojet. The accessory which is used in turbojet to get instant or high thrust and high Mach number is called multi-stage compressor, turbines with heat exchanger, afterburner, centrifugal compressor.
Sir, afterburner.
Yeah. Thrust of an aircraft engine is defined as product of mass flow rate of air and difference between jet velocity and aircraft velocity, ratio of mass flow rate of air and difference between the velocities, product of mass flow rate and summation of jet velocity and aircraft velocity.
Sir, option A, sir.
Option A, yes. It is product of mass flow rate of air and difference between the jet velocity. It is given by VJ
B
minus
minus.
U. Next, propulsive efficiency of the aircraft is defined as change in kinetic energy between the inlet and outlet by thrust power, thrust by power by change in kinetic energy, change in kinetic energy by chemical energy of fuel, thrust power by chemical energy of fuel.
Sir, option B, sir. Thrust per divided by changing kinetic energy between inlet and outlet.
Yeah. Option B is go to the next problem. Consider an ideal gas turbine cycle with two stages of compression and two stages of expansion. The pressure ratio across each stage of the compressor and the turbine is 3. The air enters the pressure ratio at each stage of compressor and turbine is 3. The air enters each stage of the compressor at 300 Kelvin and each stage of the turbine at 1200 Kelvin. Determine the um, back work ratio and the thermal efficiency of the cycle, assuming no regenerator is used. And second case, a regenerator with 75% effectiveness is used. Use specific, use variable specific heats. I think we can use a constant specific heat and then solve. stage of compressors and two stages of turbine. Then we have then we will have an heat exchanger to heat out, and then there is a second stage compressor C2. So this is 1, 2, 3, and then we have a combustion chamber, main combustion chamber CC. This is at 4 and this is 5. Then we have a turbine 1 which expands to a stage 6, and then there is an afterburner or a reheater, and then we have another turbine T2, and then it is given to atmosphere. So if you have to plot this in a TS diagram, we will first compress from 1 to 2, and then at the same pressure it is cooled down to the same temperature, because both the compressor has an intake temperature of 300 Kelvin. And now I will again compress it. The pressure ratio is also same, 3 between the two stages of compression. And then we have the main combustion chamber, and then we expand to a pressure ratio of 3 again. This is 5, this is 6, and then we add a heat, and then so these two are at 1200 Kelvin, and then we again expand. This is 7 and this is 8. These two are now we can assume that there is no regenerator, and later with regenerator and 75% effectiveness we can. So here you can calculate the efficiency. To calculate the compressor work one, we have uh, Cp into T2 minus T1. Similarly, compression 2 is Cp into T4 minus T3. Then similarly, turbine 1 is Cp into T5 minus T6. Second turbine is Cp into T7 minus T8. Here we know T1 is 300 Kelvin, and the pressure ratio is T2 P2 by P1 is equal to P4 by P3, and this is equal to P5 by P6 equal to P7 by P8. So all these are 3, and also P3 is equal to P2, and then P6 is equal to P7. And P4 is equal to P5. So T2 by T1 is P1 P2 by P1 power gamma minus 1 by gamma. So T2 is equal to pressure ratio power gamma minus 1 by gamma into T1. So this is 300 into this ratio is 3. So we have 0.4 by 1.4. Can you get T2?
The 410.62.
410.62 Kelvin. Now similarly, if you have to calculate T4 by T3, it will be same P4 by P3 power gamma minus 1 by gamma, and these are all the same. So again T3 is also 300 Kelvin, and then this is pressure ratio is also same. So we will have the same value. T4 is also same as T2. Now T5 is known, that is 1400 Kelvin. Similarly, if you want to get T5 by T6 is equal to T5 by T6 power gamma minus 1 by gamma. So T6 is equal to T5 divided by RP into gamma minus 1 by gamma. So that is, this is 1400 Kelvin, and this is 3 power 0.4 by 1.4. And T6.
The 1022.83.
1022.83 Kelvin. So this is T6. Similarly, T7 is also for 1400 Kelvin, because the start of all the at the entry of each stage of turbine is 1200 Kelvin. So that is T7 is equal to 1200 Kelvin, and similarly we can find T8 is also 1022.83 Kelvin. Now WC1 is equal to Cp into T2 by minus T1. So that is 1.005 into T2 is 410.62 minus 300. Can you calculate this?
Sir, 111.83. 0.17.
111.15. Okay. Similarly, this is also WC2 because the initial and final temperatures are the same. Similarly, if you want to calculate the turbine work, then we will have Cp into T5 minus T6. This is 1.005 into 1400 minus 1022.83. Calculate WT
379.05.
05 kilojoule per kilogram. So the net work done is equal to 2 into WT minus 2 into WC. That is 2 into 379.05 minus 111.15. Can you calculate what done?
So 535.76.
535 point. Sorry, 535.76.
76, sir.
Okay, approximating to 8 kilojoule per kilogram. Now we need to calculate the heat supply. How do we calculate? How do we calculate the heat supply?
I don't know.
Right.
I don't know, sir.
So here we are giving heat in the combustion chamber, right? So this is one heat that we are giving in, and similarly, in the reheating also we are supplying some heat. That is QS1 and QS2. So for QS1, it is enthalpy 5 minus enthalpy 4, and similarly here is it is enthalpy 7 minus enthalpy 6. So then we can have this is Cp into T5 minus T4 plus Cp into T7 minus T6. So this is Cp into T5 minus T4 plus T7 minus T6. Qs is Cp into T5 T4 T5 minus T7 minus T6. So Cp is 1.005 and T5 is end of this value. T5 is 1200 Kelvin. 1200 minus T4 is the end of compression, right? End of compression, we had some temperature 410.62 plus this T7 is again 1400. T7 is also 1200, and T6 is we have calculated. T6 is 1022.83. Can you calculate QS?
So 1172.38.
1172.38
72, sir.
kilojoule per kilogram. And now efficiency is work done by heat supply. Work done is 535.8 divided by 1172. Can you calculate efficiency?
Sir, 45 percentage.
45%. Next, we need to calculate back work ratio. What is back work ratio?
Sir, I don't know, sir.
Back work ratio is the compressor ratio by turbine ratio. So that is like how much of work we are giving back to the system. Back work ratio. For compressor, we found we didn't calculate anything. Here it is. So it is 111.15, but we have two compressors and two turbines, so we will have 2 into 111.15 divided by for turbine also we have two similar turbines. That is 379.05. Calculate this.
That's 0.29.
0.2 29 percentage back work ratio. So it signifies that for every 1 joule of work you have gaining from turbine, 0.29 joule is given back to the compressor. Okay. Do you have any questions?
I need one more time explanation, sir.
So, in this problem, consider an ideal gas turbine cycle with two stages of compression and two stages of expansion. The pressure ratio across each stage of the compressor and turbine is 3. The air enters each stage of the compressor at 300 Kelvin and each stage of the turbine at 1200 Kelvin. Determine the back work ratio and the thermal efficiency of the cycle, assuming no regenerator used and a regenerator with 75% effectiveness is used. Use variable specific heats, but we didn't use variable specific heats. We have to use a variable specific. We need to go to the we need to use some tables for uh, where the properties of air is given. So for different temperature, we'll have different specific. But now we have taken specific heat as constant. So in the drawing, we can see the air at stage one. Uh, from one, it goes to the first compressor and then becomes stage two. from where we have intercooler, and then it is coming to state 3, and then we have a second compressor C2, and then it becomes 4, and then we have a combustion chamber, it becomes 5, and then we have turbine 6, and then reheater, and then 7, and T2, second turbine, and 8. So how I assume that we have these things are like, because it has said that the for each stage of compressor the air enters at 300 Kelvin. So that means for the first stage, if you compress like this, that means then for the second stage it has to come back to the same 300 Kelvin. That means there is some intercooling happening, and then only we can reach the same temperature at the for the start of the second stage. And then, so this is the end of second stage, and then we have a we have a combustion chamber where it takes to a temperature of say 4200 Kelvin. Again we have two stages, first expansion, and then again for the at the start of second expansion we are coming back to 1200 Kelvin again. So that is how we found that there are some intercooler and the reheater in between these compression and turbine stages. And the pressure ratio for all the stages are given as 3. All the compressors like P3, P22 by P1 is also 3, P4 by P3 is also 3, P5 by 6, and P7 by 8. Everything is 3. Now, to calculate the compression work, we have the change in enthalpy before and after the compressor. So that can be expressed by Cp into T2 minus T1 for first compressor. And for second, we have Cp into T4 by minus T3. And similarly for turbine, we have Cp into T5 minus T6. And for second turbine, we have Cp into T7 minus T8. We know that the first state, we start with 300 Kelvin. And 300 Kelvin. So we can calculate the second state temperature T2 because we know the pressure ratio. So this is the expression which relates the temperature ratio to pressure ratio. So with this we calculate the second state temperature as 410 Kelvin. And similarly, while uh, in if for the second stage of compressor, the expression remains the same. We have the same initial temperature, we have the same pressure ratio, so the final pressure at the end of second stage of compression, that is 3 4, will also be the same as T2, that is 410 Kelvin. And then with the combustion chamber we reach 1400 Kelvin, and again the we know the expansion ratio for the first turbine between P5 and P6. So we can calculate T6 because we have already known T5. So T6 we have calculated as 1022.83. And similarly the for the second stage of turbine we again come back to 1200 Kelvin, and then we will expand to a temperature of 1022.83 Kelvin. Now the compressor work can be found by Cp into the change in temperature. So that is the 1.005 into 410 minus 300, and that will give some 111.15. And similarly for the turbine, we have Cp into T5 minus T6, that is 1400 minus 1022.83. Then we get 379.05. Now, the total work done is the total turbine work minus compressor work, and that comes to be 535.8. And here, to find the efficiency, we need work done by heat supplied. For heat supplied, we have two heat that is being supplied. So one is mainly in the combustion chamber, and next is in the after heater uh, reheat. So, considering the combustion chamber enthalpy change is Cp into T5 minus T4, and similarly in the reactor it is Cp into T7 minus T6. All this temperature we already know. So, substituting that we have found Qs, that is 1172.38, and then writing this in the expression of the efficiency for work done and heat supplied, we get efficiency as 45%. Next is back work ratio, that is compressor work by turbine work, and that comes to be 29%.
Okay, sir.
Now, next we can solve the same problem by assuming a regenerator. So we have a regenerator. So this is combustion chamber and this is a regenerator. This heat is taken here. Simply this. Now the effectiveness is given by as 0.75. So what is effectiveness of the regenerator? So effectiveness is actual heat transfer by maximum heat transfer that is possible. So actual heat transfer is the temperatures that we get here. Say this will be 9, and maximum heat transfer possible is that when the temperature 9 become equal or same as the temperature at 4. I've using to use the same numbering. I've given only 4 dash in between so that the other numbers are the same, and then all the values will also be same because at T5 it is 1200 Kelvin, and then there is a pressure ratio of 3, and then everything else is same. Only that the heat given by the combustion chamber will be lesser now. So effectiveness is equal to 0.75. That is actual heat transfer is T8 minus T9. This is also T4 dash minus T4. Or we will write 4A so it will be easy to see. Raise a small dash. Okay, and now maximum heat transfer is T9 is become T4. So that is T8 minus T4. So effectiveness is maximum denominator and actually 4A minus T4. Do we know the temperature T8 and T4? I think we know everything. Only 4A is unknown, so we can calculate this. So this is 0.75. T4A is unknown, but all other temperatures are known. T4 is end of compression. This 410.62, and T8 is end of turbine, exit of turbine. That is 1022.83. Now T4A is equal to for 10.62 into 0.75, 1022.83 minus 410.62. And calculate T4A. Sorry, this is not, there is no multiplication.
So 869.77.
Yeah, so we can approximate to 870 Kelvin. Now to calculate the efficiency, we had work done by heat supply, right? What term will change now? What are the terms that will be changing now because of the regenerator? Work done is the same, right? Because the compression ratio, expansion ratio, everything is same, and the initial before compression, before turbine temperature is also same. So those things will not change. Only thing that will change is the heat supply. Heat supplied in the reheater is also the same. Only the combustion chamber heat supplied is different now. Earlier it was from 4 to 5. Now it is from 4A to 5. So then QS is Cp into T5 minus T4A plus Cp into second reheater is T7 minus T6. T7 minus T6. So this is Cp into T5 minus T4A plus T7 minus T6. So this is 1.005. T5 is 1200. T5 is 1200. Yes. T5 is 1200 minus T4 is just we calculated now 870 minus plus T7 is again 1200. T7, yeah, 1200 and T6 is 1022.83. And calculate this.
So 2004 58.17.
2458.
258.
2258 kilojoule per kilogram. What QS we had earlier? Is it 2000? Earlier we had only 1172 and now it has become 2000.
No, so 509.933.
5?
509.93.
Still, there is a problem. It is becoming less than work done itself. Button is 535, right? It is unchanged. I think here actual heat transfer is T8 minus T9. Right? 8 is higher. Now 9 has become the value of 4A. Sorry, sorry. T9. So it can also be that the problem they were asked us to use a variable specific heat, and maybe it is making so much difference. Now we have taken a constant specific heat for all the temperatures. Are you able to find some problem here?
Huh?
Are you able to find some problem?
No problem.
Like now you can see like the QS has become less than the work done. So now the efficiency if we
Yes, sir.
calculate it will be more than 100.
So I tried 2007. I'm getting again 509.97.
Hmm. I think this 870 is not right. Can you calculate this QS again? This expression. I'm getting something like 970.
That's a 971.3.
Hmm. How to do that? 971.4 I'm getting. This is 971.4. And efficiency?
Sir, 58%, sir.
Yeah, 55%. Still, we need to find this one. So probably if you give variable specific key, then we will not end up like this. I'll also try to look in. You know to follow the tables, right? Like the air property table.
No, sir.
You haven't come across.
It hasn't been taught into the class.
Sorry, it is not.
No, no, sir. It doesn't taught, sir.
So we have ideal gas properties of air here. Can you see?
Yes, sir.
So at each temperature, you will be getting the enthalpy values. So instead of directly putting 1.005 into temperature, we can have this values. So so here, if you see, it will be almost h by t is 1.005. So it is following what we are writing, right? But as we go to a higher temperature, what is it? We encounter 1200 Kelvin, right? So 1200 Kelvin, it is 1277. That is 1.064, like some 6% difference is there in the CP values. So we can try with this values, but I think we'll not have time now. So we can try with these values and then we'll see. Or if there is some other problem, we'll have them in this class. Have any questions or we can close?
Sir, I don't have any questions.
Okay. Thank you for participating. See you.
Thank you, sir.